Welcome to the last week of the class. I'm sure you're excited to get on with your summer and all the exciting things that are coming your way in life. And this has to be, for me, one of my favorite, well, it is my favorite part of the course, which is what's called a goodness of fit test. So you'll notice that all semester we've been saying, assume a normal distribution, assume a uniform distribution, assume that, but how do we actually know? And so we're actually going to do what's called a categorical, a chi-squared test, or just a plain old goodness of fit hypothesis test that's going to allow you to compare what you do observe versus what they tell you you should observe, right? If somebody tells you that COVID is spreading with an R value of 2, how do they know that, right? I mean, how do we know when we flatten the curve? How do we know that 2 meters distancing is safe? All of these things are what are called goodness of fit testing. And the first thing you're going to want to look for is something called the observed. This is clutch here. That's usually a thing. If you ever see like an observed frequency, and then you see a hypothesis test coming here as well, that's clutch. All right, so what do we have here? 20 international travelers came to Calgary. See, that seems kind of like it should be important. But as we'll see here, right, so you have 20, that's good. We have 20 people, but as you're going to see here, it doesn't come really into play. So 20 travelers came to Calgary and were all infected with a new variant of COVID. The virus spreads, like let's say, according to some epidemiologists, in the absence of restrictions, according to this equation here. So some sort of exponential growth, where X is the number of weeks and Y is the total number of confirmed infections. All right, so obviously this thing is going to be important. Social interactions were imposed. Here are the number of variant cases in the first 5 weeks following the start of the restrictions. Is there any reason to believe that social distancing is working? All right, so how would we approach something like this? So the way we're going to approach this is that we have an observed number of cases, right? There's 39 cases after week 1, 75, and so on, right? This is the actual observed cases. And what we need to figure out is, does this agree with what we should expect to see? So all of chapter 11 problems are called what's called a goodness of fit. Hypothesis testing. And this, again, is a nice little wrap up to the whole semester, because you'll notice that up until now, we've always just been saying, assume a normal distribution. Or we've said, assume a Poisson distribution. Or assume a binomial, or whatever it is, right? Assume a uniform distribution. And obviously, the big problem here is that we're assuming, right? I mean, if there's anything this course should have taught you already, is that that's a bad idea, right? We don't want to be making assumptions here. And but how can we therefore test for a normal distribution, test for a Poisson distribution, test for a uniform distribution? That's what we're doing. We're in chapter 11, we're testing for how well a distribution fits what we assume is going to be. So in this case here, we're assuming this exponential distribution, right? If you have something that is y equals, if you put that in your graphing calculator, it's exponential, right? It would look something like, exponential distributions are scary. That's why you have to, that's why these COVID restrictions are so frustrating, because we don't see this. And that's good, right? You put in these restrictions so you don't get an exponential distribution, right? It's terrifying. Right? If you go back and look at your Desmos, I mean, look at that thing. It's terrifying, right? We're always stopping at about here, right? It kind of goes up like this, and then thank God we usually we flatten the curve with these restrictions or the masks or vaccines or whatever we're doing here. We never see this, thank God. But that's what would happen, right? That's not really communicated properly in the media, if you ask me. But we always say, hey, it's not that bad, and then kind of levels off. Are these things working? Because it's easy to say it's not working, right? If it's again, so if they do experiments where they don't do anything, in monkeys or rats or whatever they do, and they see these types of curves. Now, the question is, if it's going to follow an exponential curve, what should we see? What would we expect to see? And the question is when can we say we've actually kind of flattened the curve, right? Hopefully what we see, hopefully this is what's observed. And then some restrictions are put into place. And then you want to say at what point, can we say that we've flattened the curve? Because you see this all the time right, in the media, right? They say we just got to start flattening that curve. Well, how do you know when you're flattening the curve? When can you ease the restrictions again? These are all the calculations that are going into play here. And it's always, the null hypothesis is it always equals something, right? And so in this case, it's going to be a normal distribution or an exponential distribution, right? The distribution is exponential. When it comes to viral transmission. The alternative hypothesis is that it is not. We've changed it. It's flattening. You could say, but again, we're always supposed to use some sort of equal thing. So you could just say distribution is not exponential, or you could say flatter, whatever you want to say. It doesn't really, usually you have to have a not in this kind of thing. I'll just go we can just say it is not. That's good enough. Distribution is exponential. And then your alternative that it is not this. This is always going to be a two-tail. It's a different type. As we'll see today, we use what's called a chi-squared test, which is all we're testing for is if there's some sort of significant difference between observed and expected numbers. What's first? Well, first thing we should really do is figure out what should we expect, right? So again, if this is what we observe, what would be the expected values? And usually this is the first calculation. If you look at all the practice problems that I've posted on the website for chapter 11, you usually have to calculate the expected frequencies. So these are always frequencies based off of what the distribution should be, right? So again, if they said normal distribution, then you'd have to figure out what would you expect if it was normally distributed. And I'll do one of those right after this. Same thing with Poisson. So if here we have the exponentials, so all we have to do is figure out what would we expect. And so you can use Excel for this because it's easiest. Okay, so expected frequency. Um, and then this is the category, or so we'll see here the category number. There's 5 categories because there was 5 weeks. In this case, the categories are the weeks. In other words, if there's a given week that doesn't have that where the expected value is significantly far enough from what we observe, then we can probably say something is working, or the virus is just dying or whatever. Again, we can't say causation, but we can definitely say correlation. If things were not working, in other words, if social distancing was not implemented, this is what you would expect. An exponential growth like this. Now, this is not what we saw, right? This is our projected. Okay. But what did we observe? Well, we observed 39, 75, 122, 201, and 312. So when you first look at it, you're like, okay, that's cool. This looks pretty good, right? There's obviously some sort of change. The first 2 weeks is not really that different. But again, we're trying to actually quantify things in this course, right? You're not just trying to say, like, okay, maybe it worked in week 4. You want to say, when can we say it worked? When did this start working? Because then, as everybody knows, a week is a long time to close down businesses and so on and so forth. And so it matters if it's the 3rd or the 4th week. So when can we say this actually took effect? I mean, it even looks like it worked a little bit right here, but is that statistically significant? So with all hypothesis testing, after you've figured out what you're testing for, so in other words, is it exponential or not, you're going to figure out some sort of critical score. And with goodness of fit testing, we use what's called a chi-square distribution, which is new. And like all critical scores, you find them on a chart, right? The easiest way is, before we do any calculation, the critical score, we have to figure out what level of testing do we want to do here. Now, I believe they tell us 0.02. And so you would go to your formula sheet. It's table 3 right here. So this is the business we use for chapter 11 problems. Goodness of fit follows the chi-squared distributions, where we're just looking for, because it's squared, essentially, we're just looking for an absolute difference. Okay, so degrees of freedom in this case is a little bit different here as well. So degrees of freedom, when using this chart, is the number of categories minus 1. And the symbol for categories, if you remember from chapter 2, is K. And again, so in this case, the categories, we're testing to see if the expected versus the observed number of infections each week is significantly different. And then so you would say, we did a 5-week test, and so you have 4 degrees of freedom. And then you hunt around for 0.02, and then you run into a problem because this has 0.025 here. Maybe we got 0.05, we got 0.025, getting closer. But then you'll notice 0.02 is missing. So it's going to be somewhere in between here, right? So we could actually put this right in there. I mean, we can just again, we could use Excel. I'll show you how to use Excel to exactly figure this out in 1 second. But even if you just did this, right, you said, okay, I know it's somewhere between 11 and 13, and you can kind of worry about those details later. Again, you can do this with the other type of hypothesis testing we do as well. Again, I'm just really showing you one approach. But our rejection region here, so it's not a normal distribution. It doesn't really matter, but you'll notice the chi-squared is skewed to the right. There's a long tail here with chi-squared. And let's just say we're going to use, there's an alpha, there's a critical score here, and there's a critical score here, let's say. Right, this would be 0.01. Here we have 0.025, right, as rejection areas here. But, so this was what? I got 11, I have, so 13.3 and 11.1. Now, again, this is a little bit like, okay, we don't have the exact value. What if it's close, right? What if it's close? Well, then we're going to have to worry about something. But I mean, if we get a value of 10 as our test score, then, it's not a big deal. It doesn't pass any of these tests. This one, 0.025 as an alpha value. Okay, and then 0.2 would be somewhere in here. Anyways, the point I'm trying to make here is that we don't have an exact value. So why don't we just use Excel? Right? Why don't we, Excel can help us solve this by doing this. You go equals chi squared test, then we're going to go inverse right tail, and then they want your alpha value and then degree of freedom. So you could do that right here. You can say, well, my critical score is going to be this one here, chi squared inverse right tail. And then you can get your exact probability. And as you see here, it's 11.7. And that makes sense, right? It is somewhere between these two values. This totally makes sense. It would be closer to 0.025, right? So your actual value here of 11.67 is somewhere in here. And again, it makes sense based off of what we know from that primitive chart they give us as well, right? It's somewhere in here. Okay, and now we have that value. All right, that was a long-winded way of showing you that once again, Excel is better than what they did in the past. But in the old days, you'd have to do this. Like when we gave tests inside of the gymnasium on paper-based, and you're only allowed to use your scientific calculator, you would pick these two numbers out, and so that's why I wanted to show you them. Okay. Again, it's good to know how to use charts and that kind of thing. All right, so let's get down to the meat of the matter. So we've done all that. We haven't done any calculations yet, right? So let's do our actual test score, just like with all hypothesis testing. And here the formula is your chi-test is going to equal the sum of observed minus expected squared over expected. And that formula you can see in your formula sheet, in case you forget it. We don't need that. So this is the last one, your last formula. All right. So let's do that. Obviously, this is going to be a better situation for Excel. So you just kind of go over here and you say, all right, what is our observed minus the expected? And you would say, I don't know, just put it in. Right? I observed 39. I expected 40. So here's quite small, as you would imagine, right? If you just get one person different, you don't, that's not going to be very significant. Oh, still pretty insignificant. Still, at this point, you still can't say it worked. So after 3 weeks, right? Because if you sum all these together, you still don't have, you're not bigger than your critical score, right? Your critical score is 11.67. So even after 3 weeks, you say, we still haven't seen a significant difference at any one level. But right around the fourth week, as we're going to see here, this thing jumps, right? All of a sudden, this thing just jumps at the fourth week. And obviously this one where it cuts it in half, this is a significant difference for sure. But now basically in other words, our test score is 221, 221. And that's going to be way the heck over here. We're knocked it out of the ballpark. Right? It's way in the rejection zone. And so, just like everything else, right? Because the test is greater than the critical, reject the null hypothesis, which indicates that we have sufficient evidence to show that uh, something is impacting the virus reproduction, right? So again, you can't really say it's because of the restrictions, it might be because of something else, but something happened. I mean, you could even say it's slowed down because it's definitely all the numbers are lower. So you could say that the viral replication has been hampered or something like that. Now, of course, you could always, the other thing too is the p-value method offers a lot of advantages here, right? You could actually figure out how sure you actually are, right? Instead of doing the test score here, or sorry, you can take this at the test score and instead of doing this critical score business where I spent all this time trying to figure out what the heck is my critical value, instead of trying to worry about the critical value, let's just figure out the p-value of this, right? Your other strategy could have been, what is the p-value of a 221? In other words, what is this area of a 221, right? What would be the 221 area over here? And you could use that by going chi-squared regular distribution, right tail, and then putting in your values of, I think they want, in this case, it's the x value, so I'd put in 221. Right, so if you want to figure out the p-value, you would say equals chi distribution right tail, degrees of freedom. Well, I'm going to go, so basically 221.37 or whatever I have here, 3781, and then 4. Wow. What did I do there? 221. I guess it makes sense. It's a lot of distributions, isn't it? Here, if your critical score is 11, this one's this guy. That is ridiculously small. All right. Well, I guess we're very confident it's not exponential, but it's not quite zero. But the idea is that this is ridiculously small. I guess you can just do what we've always been trained to do when you have really ridiculous values like that. You can just say it's well, whatever the smallest one is, 1, 2, 3, 4, I think. Or it's less than that anyways, but right, according to our chart, that's usually we're 99.99% sure that this thing is not is not exponential. Right? That's all we can really say. We can just say it's not exponential, which basically means that something's working because we know that if nothing was working or if the virus was just kind of burning through us, it would follow this kind of trajectory. So the hardest part with all of these questions is trying to figure out the expected frequency. So if you look at the handout that I So I posted a bunch of questions here on, some people have been already asking me for, extra questions and things like that. If you go to class materials, so once you've done all the Pearson ones, right, on the Pearson website, once you're done that, you can go here and check out any chapter. This is anything that's, on the final, basically chapters 4 to 11. You can find some extra stuff here. These are all final exam style questions that I would consider giving, but as you'll see, they always give the observed in most cases. And then they give you some sort of expected distribution or frequency, and you have to figure out the expected frequency. Sorry, they'll give you the expected distribution or the expected proportions, and you usually have to calculate the expected frequency to do your chart. Like this is a classic one too, where you roll a dice 48 times, and then you have to test whether the dice is fair. This is actually a really good type of question as well. So here, when you have a dice question, right, again, you have to figure out what dice questions, you always have to figure out what is the expected distribution. In the previous example, it was exponential, right, according to y equals 2 to the power of x. And then once you have the expected distribution, then you can calculate. The next step after that is, once you know the expected distribution, then you can calculate the expected frequency. Because once you get the frequency, then you can compare it to the observed frequency. And you'll notice the frequency is the key there. Compare to the observed frequency, and this gives you your test score, right, when you do that equation. So in this case here, right, with the dice questions, what would you expect if I just roll a dice 6 times or 30 times, right? If I roll a dice, let's say 30 times, what would I expect? Well, I would expect, if it's a 6-sided die, then each number, expect a uniform distribution, right? If you roll, you know what I'm talking about with a dice, right? I'm just talking about like one of these when you're playing Yahtzee. How many times should you get 2? Well, 1 in 6, right? The probability is 1 in 6. You would expect a uniform distribution. Right? And we can just conduct that experiment really quickly using Excel, right? You can just say, in this case, the categories would be the number, the outcomes, right? How many times should I see 1? How many times should I see 2, 3, 4, 5, and 6, right? Well, you expect that a sixth of the time. In other words, if the sample size is 30, I would expect, well, 30 divided by 6. That's the hardest part there, is figuring this out, right? You're like, okay, I would expect a uniform distribution, and it takes a little bit of a thought process when, you have dice questions, or with Poisson distribution, you'd have to use the Poisson equation to figure out how many times you expect things to happen. Same thing with normal. I'll actually save the normal distribution one for tomorrow, because that's a little bit more involved. You have to use z-scores to figure out what you would expect. But this is usually the hardest part, is the expect. And then, so let's say you roll the dice 30 times. So you can simulate this, or the same question here could be, is the random number generator in Excel actually work, right? Let's say I want random numbers. What would you expect if I just rolled the dice? This simulates dice right here, right? If I did this 30 times, what would I expect to see? I would expect to see random distribution. In other words, a uniform distribution. There's no reason to roll a 2 any more than you would roll a 3. right? If I just roll the dice once, I get the number 2. If I roll the dice 2 more times, and so on, all the way to 30. Let's say I roll the dice 30 times. Let's take it all the way up here. Do it again, right? Let's go to 30. Okay, so here I rolled the dice, right? 30 times. And let's just copy and paste this so it stops changing. Okay, get rid of that because it's distracting. Right, so here I have 30 rolls of the die. Is this a norm? Is this what I would expect to see? Or is Excel lying to me, for example? Right? Is Excel, is their random number generator broken? We can test that right now. So let's test it out. So what do I actually observe? Because I performed the experiment, and what do I observe? Well, how many times did I roll a 1? I guess this has to be the outcome or the roll or the category, right? This would be the category. 1, 2, 3. Oh, I already have it here. 1, 2, 3, 4, 5, 6. Can delete that. So what do I actually observe? Well, let's count. Count if this equals 1. I only rolled 1, 1. Isn't that crazy? Right? So this thing already looks broken. Uh-oh. So here's the question. Can I sue Microsoft to say that you don't have a random number generator? You're actually you have a loaded dice. How many 2s did I roll? Well, that one looks pretty good. How many 3s did I roll? Well, that was bang on. How many 4s did I roll? That looks pretty good. How many 5s did I roll? Uh-oh. Now it's looking sketchy, right? I've rolled 8 5s. And how many 6s did I roll? So this already looks pretty loaded, right? Because you say, well, you rolled 8 5s and 8 6s and only 1 1. But the question is this statistically significant or is this just luck, right? If you ever play Yahtzee, sometimes this is how, sometimes you get hot, right? And you get a whole bunch of 6s. So is there, like if I went to your house and I played with this dice and I lost all my money, could I complain? Well, let's find out. So you want to figure out, is the observed value any significantly different than my expected values? Okay, looks okay. So 3.2, that's not too bad. So why is this not any more significant? Because I didn't roll it a lot, right? I was expecting 5, I get 8. My total sample size here is only 30. So the weirdest one, as you would expect, is the first one, right? This one's really weird. 5 and 1. I didn't get a lot of 1s, but that gives me a chi-squared value of this. Now, what's my total? Because that's how you figure out your actual test score, is you have to look at all the categories. Is there any, you have to add up the differences between all of them. And now I have only a test score of 7.2, which is low, right? It's not going to meet the critical scores, right? The critical score, again, right? So I know that I used my test score because I used Excel to give me a 7.2. Now, what's the critical score? I don't know. Let's pick alpha 0. Let's say 0.5 or 0.01. Let's go 0.5. Here, what's the degree of freedom here? 6 of 5. 6 categories, degree of freedom of 5.05, right? And because that's going to be nice, again, I just chose this randomly. Use table 3 in your booklet. So let's go 5 degrees of freedom, 11.07. And again, so here's an example where I cannot reject the null hypothesis. I couldn't even do it if it was this, right? My value is so low. But again, because I have 11.1, here's my rejection zone. Where am I? 7.2. I guess I'll have to work another day as a teacher and I can't sue Bill Gates. But one day I've been waiting to try, I've been doing that experiment for, for a couple of years. It's never worked. It's always been random. But one day my class will watch me defeat the computer and prove that it's not actually random. But I've never seen it. You can try this as much as you can. This is a random number generator. Once you start understanding the logic behind some of these processes, you'll find that it becomes more entertaining as well. So you have to wait a while.